December 3, 1944. Rechlin-Lärz Aerodrome, 90 kilometers north of Berlin. Hauptmann Franz Stigler walks across frozen concrete toward an aircraft that shouldn't exist. The P-51D Mustang sits under guard in a maintenance hangar, captured 3 days earlier when its pilot, 2nd Lieutenant Thomas Harrell, made an emergency landing after his engine seized over Brandenburg. The aircraft is intact. More importantly, its cooling system is intact, and Stigler has been ordered to examine it. Stigler is 27 years old, a Luftwaffe fighter ace with 42 confirmed kills, and he has spent 3 years trying to shoot down Mustangs. He knows their performance envelope better than most Allied pilots. He knows they can cruise at 380 miles per hour at 25,000 feet. He knows they can escort bombers all the way to Berlin and still have fuel to fight. And he knows that according to every aerodynamic principle, the Luftwaffe's engineers understand none of this should be possible with a liquid-cooled inline engine. The German engineering establishment has spent a decade refining liquid-cooled fighter design. The Messerschmitt Bf 109, the Focke-Wulf Fear 190D, the Heinkel Hay 100 all represent the pinnacle of what German thermodynamics and aerodynamics can achieve, and none of them can match the Mustang's combination of speed and range. The 109 is fast but short-legged. The 190D has power but burns fuel like a blast furnace. The Mustang does everything and makes it look effortless. The question that haunts German fighter pilots isn't whether they can outfly the Mustang. The question is how the Americans built an engine cooling system efficient enough to sustain 440 miles per hour in level flight without the radiator drag-destroying performance. Because the math, as every Luftwaffe engineer knows it, says that shouldn't be possible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Stigler's orders come from Oberst Gordon Golob, commander of fighter operations at Rechlin. Golob wants a detailed technical assessment of the Mustang's cooling system. Not the usual combat evaluation, pilots have filed hundreds of those. Golob wants engineering analysis. He wants to know what the Americans did that German designers missed, and he wants to know if the Luftwaffe can replicate it. Stigler brings 2 men with him, Hauptmann Heinz Noack, another ace with 33 kills, and Oberleutnant Werner Mulders, nephew of the late Werner Mulders, and a former engineering student at the Technical University of Berlin. Between them, they have 112 confirmed aerial victories against Allied aircraft. They have flown against Mustangs over France, over Germany, over the Baltic. They know what this aircraft can do in combat. Now they need to understand how it does it. The hangar is unheated. Their breath fogs in the December air. The Mustang sits on its tricycle landing gear, with its cowling panels already removed by Luftwaffe ground crew. The Packard-built Merlin engine is exposed, a 12-cylinder V configuration that produces 1,490 horsepower at 25,000 feet. The Americans call it the V16507. It's a license-built copy of the British Rolls-Royce Merlin 66, manufactured in Detroit by Packard Motor Company and shipped to North American Aviation's plant in Inglewood, California. Stigler knows Merlin's reputation. The engine powers the British Supermarine Spitfire, the Hawker Hurricane, the Avro Lancaster bomber. It's reliable, powerful, and for a liquid-cooled design, remarkably tolerant of battle damage. But the Spitfire, even with a Merlin, tops out around 400 miles per hour in level flight. The Mustang, with essentially the same engine, hits 440. That extra 40 miles per hour represents a massive difference in combat capability. It means the Mustang can chase down anything the Luftwaffe flies. It means German pilots can't run. And it means something about the American cooling system is fundamentally different. Noack circles the aircraft, studying the radiator installation. On German fighters, the radiators are mounted under the nose or in the wing roots. The Bf 109's coolant radiator sits directly beneath the engine in a bulky chin installation that creates significant drag. The VW 190D's radiator is buried in the fuselage behind the cockpit, requiring long coolant lines that add weight and complexity. Both designs compromise either drag or weight. You can't optimize both. The Mustang's radiator sits in a streamlined scoop beneath the fuselage, aft of the cockpit. The scoop is shaped like an inverted teardrop, smooth and carefully contoured. Air enters through an intake at the front, flows through the radiator core, and exits through controllable flaps at the rear. The entire assembly looks almost like an afterthought, a small appendage that couldn't possibly handle the thermal load of a 1400 horsepower engine running at full power. Melders kneels beside the radiator scoop and runs his hand along the intake duct. The metalwork is precise, every seam smooth, every rivet flush. He looks up at Stigler and says something that will appear in his report 3 days later. This is not a radiator installation. This is a jet engine. He's not being metaphorical. The radiator scoop on the P-51 uses a principle called the Meredith effect, named after British engineer Frederick Meredith, who described it in a 1935 paper. The principle is simple, in theory, extraordinarily difficult in practice. When air flows through a duct and is heated by a radiator, it expands. If the duct is shaped correctly, that expansion accelerates the air, and the accelerated air exiting the rear of the duct can generate thrust. Not a lot of thrust, maybe 200 or 300 pounds at high speed, but enough to offset most of the drag created by the radiator installation itself. German engineers know about the Meredith effect. It's in the textbooks, but no German aircraft has ever implemented it successfully in combat. The ducting has to be perfect. The radiator has to be exactly the right size. The exit flaps have to be controllable to maintain optimal pressure ratios across different speeds and altitudes. Get any of it wrong, and instead of recovering drag, you create more. The Bf-109's engineers tried a Meredith effect duct in 1939. The prototype overheated at low altitude and generated so much drag at high altitude that it was slower than the standard design. They abandoned the concept. But the Mustang makes it work. Stigler can see it in engineering. The intake duct is shaped to decelerate incoming air smoothly, converting velocity into pressure without creating turbulence. The radiator core sits at the point of maximum pressure, ensuring maximum airflow through the fins. The exit duct expands gradually, allowing the heated air to accelerate without separation, and the exit flaps, controlled by a thermostatic actuator, modulate the back pressure to maintain optimal thrust recovery across the entire flight envelope. It's brilliant, it's elegant, and it shouldn't work this well. Noak asks the obvious question: how did the Americans get this right when German engineers couldn't? Stigler doesn't have an answer. Mulders suggests it might be manufacturing precision. The Meredith effect requires tolerances measured in millimeters. If the duct shape deviates even slightly from the design, efficiency collapses. Maybe American manufacturing technology is better than German intelligence assessments indicate. They spend an hour measuring the radiator installation. Mulders uses calipers to record the intake duct dimensions, 187 millimeters wide at the entrance, expanding to 234 millimeters at the radiator face. The exit duct starts at 219 millimeters and expands to 261 millimeters before the flaps. Every measurement is recorded in a notebook that will be typed up and sent to the Messerschmitt Design Bureau in Augsburg. Then they open the coolant system. The header tank, mounted directly behind the propeller, holds 4 gallons of ethylene glycol mixture. Coolant lines run from the header tank down both sides of the engine block, through passages in the cylinder heads, then back to the radiator via 2-inch diameter aluminum tubes. The entire system operates at 30 pounds per square inch of pressure, allowing the coolant to run at temperatures up to 110 degrees Celsius without boiling. What surprises Stigler is how vulnerable it all is. The coolant lines are thin-walled aluminum tubing, maybe 2 millimeters thick. A single rifle-caliber bullet could puncture them easily. The header tank has aluminum walls barely 3 millimeters thick. A 20 millimeter cannon shell would shred it. The radiator core itself is a honeycomb of brass tubes and aluminum fins, delicate and exposed in the belly scoop. This is the contradiction that German pilots have exploited for 18 months. The Mustang is fast, but it's fragile. Aim for the belly scoop, and you can drain the cooling system with a single hit. The engine will seize in minutes. The pilot will go down. It's a tactic every Luftwaffe pilot learns. Don't chase the Mustang in level flight because you can't catch it. Don't try to outturn it because the Merlin's power-to-weight ratio is too good. Instead, get below it, come up from underneath, put a burst into the radiator scoop, and watch it stream white glycol vapor all the way to the ground. Noak has killed 4 Mustangs that way. Stigler has killed 7. Every pilot in this hangar knows the cooling system is the Achilles heel. But, standing here, looking at the engineering, Stigler realizes something that makes him profoundly uncomfortable. The Americans know it too. They designed this cooling system knowing it was vulnerable, and they decided the performance gain was worth the risk. That's not how German engineering works. German doctrine prioritizes survivability, armor plate, self-sealing fuel tanks, redundant systems. These are design requirements, not options. The W190 has 14 millimeters of armor plate behind the pilot and armored glass 3 centimeters thick. Its fuel tanks are surrounded by rubber bladders that seal bullet holes automatically. The BMW 801 radial engine can lose 3 cylinders and still fly. When you shoot a 190, it takes the hit and keeps fighting. The Mustang has minimal armor. The cooling system has no redundancy. One hit in the wrong place is fatal. But that vulnerability bought 40 extra miles per hour and 600 miles of additional range. The Americans made a calculated trade. Accept fragility in exchange for performance that no armored aircraft could match. Mulders traces the coolant lines with his finger, following their path through the airframe. He stops at a junction where 3 lines converge near the firewall. He looks at Stigler and says, "1 20mm shell here, and the entire system drains in 90 seconds. Stigler nods. He's put 20mm shells into that exact location. Twice. Both times the Mustang went down trailing vapor. Both pilots bailed out over Germany. One was captured. One died when his parachute failed to open fully. That was over Magdeburg in September. The pilot's name was Lieutenant Howard Chen. Stigler remembers because Chen had fought well, had tried to climb away using the Mustang's superior power-to-weight ratio, had almost made it to altitude before his engine temperature spiked past maximum and the Merlin seized. Standing in this hangar, looking at the system that killed Chen, Stigler feels something he doesn't have words for. Not quite guilt he was doing his job. Chen was doing his, but a kind of grim recognition. This cooling system represents a philosophy of war that's alien to German thinking. The Americans built an aircraft that wins by being faster and going farther, even if that means their pilots die when they take hits that a German pilot would survive. It's a bomber escort fighter that accepts pilot casualties in exchange for protecting the bombers. The math is cold. Lose 1 Mustang pilot to save a B-17 with 10 crewmen aboard. The trade is worth it. From a strategic perspective, it's logical. From a pilot's perspective, standing here looking at 2mm thick coolant lines, it's horrifying. Noak moves to the engine itself, studying the Packard Merlin's construction. The engine block is cast aluminum, lighter than the cast iron blocks German designers favor. Each cylinder has a steel liner pressed into the aluminum casting, providing wear, resistance without excessive weight. The crankshaft is forged steel, machined to tolerances that Noak estimates at less than 0.05 of a millimeter. The connecting rods are H-section forgings, maximizing strength while minimizing weight. The supercharger assembly sits at the rear of the engine, a 2-stage, 2-speed design that compresses intake air progressively. The first stage runs continuously, driven by the crankshaft through a gear train. The second stage can be engaged or disengaged depending on altitude. Below 15,000 feet, the pilot runs single stage. Above 15,000 feet, he engages the second stage, and the engine continues producing full power all the way to 25,000 feet. German engines use similar supercharging principles, but the Merlin's implementation is more refined. The intercooler between the two supercharger stages is compact and efficient, cooling the compressed air from the first stage before it enters the second. That cooling increases air density, allowing more oxygen into the cylinders, which means more fuel can be burned, which means more power. The entire thermodynamic cycle is optimized for high-altitude performance. Noak asks about fuel consumption. Mulders pulls a technical manual from his bag, captured American documentation that came with the aircraft. He flips to the performance charts and reads aloud. At 25,000 feet, cruising at 300 miles per hour, the Merlin consumes 72 gallons per hour. The Mustang carries 184 gallons internally, plus two 108-gallon drop tanks. Total fuel capacity, 400 gallons. That gives a range of 1,650 miles with reserves. 1,650 miles. That number sits in the cold air between them like an accusation. The Bf-109G6, Germany's primary fighter, carries 88 gallons internally. At cruise power, it burns 51 gallons per hour. Combat radius, approximately 350 miles. The 109 can't escort bombers to Berlin and back. It can barely patrol its own airspace before needing to land and refuel. German fighters are tethered to their bases by fuel limitations, while Mustangs roam across the entire Reich with impunity. Stigler has felt this limitation in combat dozens of times. You intercept a bomber formation, engage the escorts, fight for 10 minutes, and suddenly your fuel warning light illuminates. You have to break off. You have to head home. The Mustangs don't. They can chase you all the way back to your airfield if they want. They have fuel to burn. Literally. Mulders asks the question that's been hanging unspoken. How did American engineers achieve this fuel efficiency? The Merlin isn't a particularly efficient engine by specific fuel consumption standards. It burns roughly 0.5 pounds of fuel per horsepower per hour, which is typical for high-performance engines. German engines have similar numbers. The difference isn't engine efficiency. The difference is drag. The Mustang has less drag than any fighter either side has put into production. Its laminar flow wing, designed by North American aviation's engineers using NACA airfoil research, maintains smooth airflow over a greater percentage of the chord than conventional wings. Smooth airflow means less drag. Less drag means less throttle required to maintain speed. Less throttle means lower fuel consumption. The entire aircraft is optimized for efficiency in ways German designers haven't fully grasped. Stigler walks around the wing, studying its profile. The wing is thin, just 14% thickness to chord ratio at the root, tapering to 12% at the tip. German fighters use thicker wings. The 109 is around 14.2%, because thick wings provide more internal volume for fuel tanks, landing gear, and ammunition. But thick wings create more drag. The Mustang accepts reduced internal volume in exchange for lower drag, then compensates by hanging external fuel tanks beneath the wings. It's another trade-off, another calculated compromise. The Americans seem to understand that in air combat, speed and range trump everything else. Armor doesn't matter if you can dictate the terms of engagement. Internal fuel capacity doesn't matter if you can carry disposable external tanks. Conventional wisdom doesn't matter if you're willing to challenge it. Noak points to something that makes all three of them pause. The wing's surface is almost perfectly smooth. The rivets are flush, filed down and filled so they don't protrude. The panel seams are sealed with putty and sanded smooth. The entire aircraft has been finished to a standard that German mass production abandoned in 1942. This isn't a hand-built prototype. This is a production aircraft, one of thousands built at North American's Inglewood plant, and it has surface finish quality that Messerschmitt reserves for racing aircraft. Mulders runs his hand along the wing and says, "They're not just building fighters, they're building them correctly." It's a damning observation. German fighter production in late 1944 prioritizes quantity over quality. Messerschmitt is delivering over 1,109 seconds per month, but the surface finish is rough, rivets protrude, panel gaps are measured in millimeters instead of hundredths. It's faster to build that way, it's cheaper, And when you're losing aircraft faster than you can replace them, speed of production matters more than aerodynamic refinement. But that rough finish costs performance. Every protruding rivet creates a tiny vortex. Every panel gap creates turbulence. Individually, each defect is negligible. Cumulatively, they add up to 15 or 20 miles per hour of lost speed. The Bf-109 G6 is theoretically capable of 386 miles per hour at 21,000 feet. In practice, production aircraft rarely exceed 365 because the surface finish is too rough. The Mustang, with its flush rivets and sealed seams, achieves its theoretical performance in service. 440 miles per hour isn't a wind tunnel number. It's what pilots actually see on their airspeed indicators in combat. That attention to manufacturing detail represents an industrial capacity Germany can't match anymore. Stigler knows this intellectually, but seeing it manifested in aluminum and steel makes it visceral. The Americans can afford to build fighters with hand-filed rivets and perfectly sealed seams. They can afford to optimize every detail because they have the industrial capacity, the trained workforce, and the time. Germany has none of those luxuries. German factories are being bombed around the clock. Skilled workers have been drafted into the Wehrmacht. Production schedules are compressed to the point of breaking, and still, the Americans are outbuilding them, 10-1, while maintaining higher quality standards. The three pilots spend another hour examining the Mustang. They measure the propeller an 11-foot, 2-inch diameter Hamilton Standard constant speed unit. They inspect the gun installation, 6 50 caliber Browning machine guns, 3 per wing, with 400 rounds per gun. They study the cockpit layout, the instrument panel, the control arrangement. Everything is functional, logical, designed for a pilot to operate under stress without confusion. Then Melders opens the aircraft's technical manual to a section labeled Emergency Procedures and reads aloud a passage that stops all three of them cold. In the event of coolant system damage, reduce power to minimum cruise, open radiator flap to maximum, monitor engine temperature continuously. Maximum permissible temperature is 110 degrees Celsius. If temperature exceeds 110 degrees, engine seizure is imminent. Pilot should prepare for forced landing or bailout. Expected time from coolant loss to engine seizure, 3 to 7 minutes depending on power setting and damage severity. 3 to 7 minutes. The manual states it plainly, without euphemism. If you take a hit to the cooling system, you have 3 to 7 minutes before your engine destroys itself. 3 to 7 minutes to decide whether to bail out over enemy territory or try to glide to friendly lines. 3 to 7 minutes before you're either dead or a prisoner of war. German technical manuals don't include passages like this. German manuals assume aircraft will be damaged in combat and will limp home. They include procedures for flying with damaged control surfaces, with one elevator jammed, with partial hydraulic failure. But they don't include procedures that amount to, your aircraft is now dying and you should prepare to abandon it. Noak looks at Stigler and says what they're all thinking. They sent pilots into combat knowing this. Stigler nods slowly. American commanders knew the P-51's cooling system was vulnerable. They knew one hit could bring the aircraft down. They knew pilots would die because of this design choice. And they deployed the aircraft anyway because the strategic value escorting bombers deep into Germany outweighed the pilot casualties. It's ruthless calculus. It's effective calculus. And it's completely contrary to Luftwaffe doctrine, which has always emphasized pilot survival above mission completion. German pilots are trained for years. Losing an experienced pilot is a strategic disaster that can't be easily replaced. American pilots are trained for months, and when one is lost, another arrives from the training pipeline within weeks. The Americans can afford to accept higher pilot casualties because they have an inexhaustible supply of replacements. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination concludes at 1400 hours. Stigler, Koeug, and Mulders walk back across the frozen concrete toward the operations building, where they'll file their report. Behind them, Luftwaffe ground crew begin covering the Mustang with tarps. It will be transported to Messerschmitt's facility in Augsburg for more detailed analysis, then likely destroyed to prevent it from being recaptured if Soviet forces advance into the area. None of the three pilots speak during the walk. There's nothing to say that won't sound like defeatism. They've just examined an aircraft that represents everything Germany is losing: industrial capacity, engineering refinement, strategic vision, and the cold willingness to accept casualties in pursuit of operational objectives. Stigler filed his report that evening. It's 7 pages, typed by a clerk from his handwritten notes. The core findings are technical measurements, specifications, observations about the cooling system design and the Meredith effect radiator installation. But the final paragraph, which Stigler writes himself in longhand, captures something the technical details can't convey. The P-51D represents a fundamental difference in design philosophy. Where German engineering prioritizes pilot survival and aircraft robustness, American engineering prioritizes mission performance and operational range. The aircraft's cooling system is its greatest vulnerability and its greatest achievement. It enables performance that our interceptors cannot match, but condemns damaged aircraft to rapid loss. The Americans have accepted this trade consciously. They have built an aircraft that wins wars but costs pilots. Whether this represents superior strategic thinking or callous disregard for human life, I cannot say, but it is effective, devastatingly so. The report goes to Oberst Golob, then to the Reichsluftfahrtministerium in Berlin, then to Messerschmitt's chief engineer. Nobody responds. By December 1944, reports about captured enemy aircraft were academic exercises. The Luftwaffe doesn't have the fuel to fly the fighters it already has. The industrial capacity to implement design improvements doesn't exist, and the Americans are producing Mustangs faster than Germany can shoot them down. Hauptmann Heinz Nock flew his last combat mission on January 17, 1945. He's shot down by a Mustang over Braunschweig. He bails out and survives with a broken leg. The Mustang that shoots him down fires from below, a deflection shot that rakes his 109 from tail to nose. Nock sees the tracers coming but can't evade. His aircraft catches fire immediately. He jettisons the canopy and rolls inverted. He drops away and pulls his ripcord at 4,000 feet. The parachute deploys and he drifts down, watching his fighter auger into a field 3 kilometers away. He lands in a farmer's field near Helmstedt. British troops found him 2 hours later. He's taken a prisoner and spends 4 months in a POW camp in Belgium. During interrogation, a British intelligence officer asks him about German assessments of the P-51. Nock tells him about the examination at Rechlin. The officer asks what Nock thought of the Mustang's design. Nock says, "It's the best fighter aircraft I've ever seen, and it should never have been built the way it was built." The officer doesn't understand. Nock explains, the cooling system, the vulnerability, the 3 to 7 minute death sentence. The officer listens and then says something Knock will remember for the rest of his life. We knew, the pilots knew, but the Mustang could reach Berlin and nothing else could. So we flew them anyway. Werner Mölders survives the war. He returned to the Technical University of Berlin in 1946 and completed his engineering degree. He writes his thesis on high-altitude engine cooling systems, using his examination of the captured Mustang as a case study. The thesis analyzes the Meredith effect radiator installation and concludes that German engineers had the theoretical knowledge to implement similar systems, but lacked the manufacturing precision and testing infrastructure to make them work reliably in production. Mölders goes on to work for Messerschmitt's successor companies, eventually becoming chief engineer for cooling systems at MBB in the 1960s. He designs environmental control systems for the F-104 Starfighter and later contributes to cooling systems for the Tornado strike fighter. In a 1978 interview, he's asked about the most impressive aircraft he ever examined. He says the P-51 Mustang without hesitation. The interviewer asks why. Mölders says, Because it taught me that perfect engineering isn't about eliminating weaknesses. It's about accepting the right weaknesses in exchange for the right strengths. The Mustang's cooling system was vulnerable, but that vulnerability enabled performance nothing else could match. The Americans understood something we didn't. In war, perfection is the enemy of victory. Franz Stigler flew his last combat mission on January 20th, 1945. He lands safely at Münchenheim airfield, with 61 confirmed kills. When the war ends 4 months later, he's working as a flight instructor at a training base in Bavaria. He never flies combat again. In 1948, Stigler emigrated to Canada. He becomes a commercial pilot and eventually a businessman in Vancouver. He doesn't talk about the war publicly until the 1990, when he reconnects with Charles Brown, an American B-17 pilot whose damaged bomber Stigler escorted to safety over the North Sea in December 1943 instead of shooting it down. The story becomes famous, two enemies who became friends decades after the war. But Stigler never forgets the captured Mustang at Rechlin. In a 1992 letter to a military aviation historian, he writes about that December day in 1944 when he examined the cooling system and realized what it meant. "We thought we were analyzing an enemy aircraft. Really, we were reading our own obituary." The Mustang represented everything Germany had lost by then: industrial capacity, engineering discipline, strategic clarity. But more than that, it represented a willingness to make hard choices. The Americans built an aircraft that would get pilots killed, and they did it anyway because the mission mattered more than individual survival. That's how you win total wars. That's how you defeat nations that prioritize preservation over victory. We learned that lesson too late. The captured P-51D at Rechlin was destroyed in February 1945 when Soviet artillery began shelling the airfield. It never made it to Augsburg for detailed analysis. The reports Stigler, Koch and Mulders filed are preserved in the Bundesarchiv Militärarchiv in Freiburg. They total 43 pages, across 3 separate documents. Most of the content is technical specifications, but scattered throughout are observations that reveal what those German pilots understood when they examined that cooling system. They understood they were looking at a weapon designed by people who thought differently about acceptable losses. They understood the cooling system's vulnerability wasn't a design flaw, it was a design choice. And they understood that choice had given the Americans an aircraft capable of accomplishing missions German fighters couldn't match. The technical implications of what Stigler and his colleagues discovered went far beyond the immediate tactical situation. The Meredith effect radiator installation represented a convergence of aerodynamic theory, thermodynamic engineering, and manufacturing precision that German industry could no longer replicate, even if they had the blueprints. In January 1945, Messerschmitt's design bureau received copies of the Rechlin reports. Chief engineer Robert Lusser, who had led the Me-109's development since 1934, convened a meeting of senior aerodynamicists to discuss whether similar cooling systems could be retrofitted to existing German fighters. The meeting lasted 4 hours. The conclusion was unambiguous: impossible. The problem wasn't understanding the principles. German engineers had access to Meredith's original 1935 paper. They understood that heating air in a properly shaped duct could generate thrust. The problem was implementation. The Mustang's radiator installation required tolerances measured in tenths of millimeters across ducting that ran for over a meter. Any deviation from the optimal duct geometry would cause flow separation, destroying efficiency and creating drag instead of recovering it. German manufacturing facilities in early 1945 couldn't hold those tolerances reliably. Allied bombing had destroyed the most precise machine tools. Skilled machinists had been drafted into infantry units to replace casualties on the Eastern Front. The factories still operating were focused on quantity, churning out fighters with increasingly rough finish quality, because smooth aircraft didn't matter if you had no fuel to fly them. Lusser's report to the Reichsluftfahrtministerium, filed on January 23, 1945, states plainly, Implementing Meredith effect cooling on current production aircraft would require retooling our entire manufacturing infrastructure, retraining our workforce, and diverting resources from current production for an estimated 18 to 24 months. We do not have 18 to 24 months. We do not have the resources, and we no longer have the industrial capacity the Americans demonstrated in building the P-51. The report was filed and forgotten. By January 1945, the Luftwaffe's primary problem wasn't aircraft performance, it was fuel. Germany's synthetic fuel plants were being systematically destroyed by Allied bombing. Jet fuel production had collapsed. Aviation gasoline production was at 20% of 1943 levels. The Luftwaffe had over 3,000 fighters grounded not from battle damage, but from fuel shortages. Pilots sat in ready rooms watching American bomber formations fly overhead, unopposed, because there wasn't enough fuel to scramble interceptors. When missions were flown, they lasted 30 minutes before fuel exhaustion forced pilots to land. The strategic irony was overwhelming. Germany had developed the world's first operational jet fighter, the Me-262, capable of outrunning any Allied fighter, but couldn't fuel it. The Americans had developed a conventional piston-engine fighter with a vulnerable cooling system, and they flew it everywhere because they had unlimited fuel. But the cooling system vulnerability remained tactically relevant for those missions the Luftwaffe could still fly. German pilots continued targeting the Mustang's belly scoop whenever possible. Between December 1944 and April 1945, the 8th Air Force lost 163 P-51 seconds in combat over Germany. Luftwaffe records, fragmentary and incomplete for this period, suggest approximately 40% of those losses involved cooling system damage from ground fire or fighter attack. One particular engagement demonstrated both the vulnerability and the ruthless effectiveness of American doctrine. On February 3, 1945, a formation of 48 P-51 seconds from the 357th Fighter Group escorted B-17 seconds to Berlin. The bomber formation was attacked by approximately 30 Me-109 seconds and Foe 190 seconds over Brandenburg. The Mustangs engaged the German fighters while maintaining close escort on the bombers, exactly the mission they were designed for. The engagement lasted 11 minutes. The Americans claimed 7 German fighters destroyed. The Germans claimed 6. P-51 shot down. Actual losses. Verified post-war. 5 German fighters destroyed. 4 P-51 lost. 3 of the 4 Mustangs were brought down by cooling system failures after taking hits during the dogfight. All 3 pilots bailed out over German territory. 2 were captured immediately. 1. Second Lieutenant James Morrison evaded for 3 days before being taken prisoner near Potsdam. Morrison was interrogated by Luftwaffe intelligence officers at Dulag Luft, the transit camp for Allied airmen. During interrogation, a German officer asked him about the P-51's cooling system. Morrison, following standard protocol, refused to discuss technical details. The officer said, "We already know. We've examined captured aircraft. Your cooling system can be destroyed by a single hit. Why do your commanders send you into combat in an aircraft with such a vulnerability?" Morrison's response, recorded in his post-war debriefing report, was simple. "Because we still shoot down more of you than you shoot down of us." The mathematics supported Morrison's statement. Between June 1944 and May 1945, P-51 units in Europe claimed approximately 4,700 German aircraft destroyed in air-to-air combat. The 8th and 9th Air Forces lost approximately 875 P-51 seconds to all causes during the same period. Even accounting for overclaiming standard in air combat, the exchange ratio favored the Americans by at least 3-1. That ratio existed despite the cooling system vulnerability. The Mustang's speed, range, and climb rate gave American pilots the ability to dictate engagement terms. They could attack when conditions favored them and disengage when they didn't. German pilots, flying shorter-ranged fighters with less fuel, couldn't refuse combat. They had to defend their airspace with whatever resources they had, even when outnumbered and outperformed. The cooling system's vulnerability mattered in and individual engagements, but became statistically irrelevant across thousands of sorties. Yes, a single hit could down a Mustang, but American pilots were trained to minimize exposure, to fight from positions of advantage, and to use their aircraft's performance to avoid situations where that single hit could occur. The tactics compensated for the technical vulnerability. German pilots, by contrast, were increasingly forced into desperate situations. Fuel shortages meant less training for new pilots. Veteran pilots were dying faster than they could be replaced. By early 1945, the average Luftwaffe fighter pilot had approximately 60 hours of flight training compared to over 300 hours for American pilots. The skill differential compounded the performance differential. Even if German aircraft had matched the Mustang's capabilities, the pilot quality gap would have determined outcomes. Oberleutnant Günther Rahl, one of the Luftwaffe's highest-scoring aces with 275 confirmed kills, flew against Mustangs repeatedly between late 1943 and his final combat mission in May 1944, when he was shot down and severely injured. In post-war interviews, Rahl was asked repeatedly about the P-51's strengths and weaknesses. His assessment was clinical. The Mustang was fast, had excellent range, and could fight at any altitude. Its cooling system was vulnerable, yes, but exploiting that vulnerability required getting into firing position, which required either superior pilot skill or numerical advantage. By 1944, we rarely had either. The Americans could afford to lose aircraft to cooling system failures because they had more aircraft, more pilots, and more fuel. We couldn't afford to lose anything, which meant we were fighting a losing battle regardless of technical details. Rahl's observation captures the strategic reality that Stigler, Noak, and Mulders recognized in that Rechlin hangar. The P-51's cooling system vulnerability was real, exploitable, and cost American lives, but it existed within a larger context where American industrial capacity, training infrastructure, and resource availability created advantages that overwhelmed any single technical weakness. The Americans built an aircraft that would get pilots killed and deployed it anyway, because the operational requirements escorting bombers to targets deep in Germany mattered more than minimizing pilot casualties. That calculus sounds callous when stated plainly, but it was strategically correct. The bomber offensive against German industry, enabled by long-range fighter escorts, destroyed Germany's ability to wage war. The cost was measured in hundreds of fighter pilots lost to cooling system failures and thousands of bomber crewmen lost to fighter and flak attacks. The result was the collapse of German military production and the end of the war in Europe. German engineering philosophy, shaped by resource constraints and strategic defensiveness, couldn't make those trades. German fighters prioritized pilot survival because Germany couldn't afford to lose trained pilots. They prioritized robust construction because Germany couldn't afford to lose aircraft to easily repairable damage. Those priorities were rational given Germany's situation, but they resulted in aircraft that couldn't accomplish the missions that mattered most. The Me-109, even in its latest variants, couldn't escort bombers to targets deep in enemy territory because it lacked range. The Fu-190 had power and armament but burned fuel too quickly for long-range missions. German jet fighters like the Me-262 had revolutionary performance but required specialized fuel that wasn't available in sufficient quantities. Every German fighter design faced constraints that the P-51 didn't, because the P-51 was built by a nation that could afford to accept its weaknesses in exchange for its strengths. Technical documents from North American Aviation's engineering department, declassified in the 1970s, reveal that designers were fully aware of the cooling system's vulnerability from the beginning. Internal memoranda from 1942 discuss the trade-offs explicitly. Armoring the coolant lines would add approximately 200 pounds. That weight would reduce range by roughly 80 miles and top speed by 8 miles per hour. The decision was made to accept the vulnerability and preserve the performance. Edgar Schmude, the P-51's chief designer, addressed the cooling system question in a 1973 interview. "We knew it was vulnerable. We knew pilots would die because of that vulnerability, but we also knew that without that cooling system design, the aircraft couldn't perform its mission. The bomber crews needed escorts that could stay with them all the way to the target and back. That required range and speed. Adding weight to protect the cooling system would have compromised both. So we made the choice. Optimize for the mission, accept the casualties, and trust that superior numbers and tactics would offset the vulnerability. It was cold engineering logic applied to human lives. It was also the approach that won the air war over Europe. By March 1945, the Luftwaffe was effectively destroyed as a fighting force. Fuel shortages grounded most fighters. Experienced pilots were dead or in hospitals. The aircraft industry was shattered by bombing. American fighters roamed German airspace with near impunity. Mustangs strafed trains, attacked airfields, and engaged the few remaining German fighters in one-sided combat. The cooling system vulnerability that German pilots had exploited for 18 months became increasingly irrelevant because opportunities to exploit it had vanished. You can't shoot down the enemy's vulnerable radiator if you can't get airborne to intercept them. You can't aim for their weak point if they're attacking at your airfield from 5,000 feet while you're scrambling to start your engine. Franz Stigler understood this in December 1944 when he examined that captured Mustang at Rechlin. The technical analysis was interesting. The implications were devastating. The Americans had built an aircraft with a fatal flaw and turned that flaw into a footnote through overwhelming operational superiority. They had made a conscious choice to accept pilot casualties in exchange for mission capability, and that choice had won them air superiority over the entire European theatre. German pilots respected the Mustang. They feared it. But what haunted many of them, including Stigler, was the recognition that the aircraft represented a way of thinking about war that Germany couldn't match. The Americans approached warfare as an engineering problem to be optimized. They calculated acceptable losses. They traded individual lives for operational objectives. They built weapons that would kill their own users if it meant accomplishing the mission. That ruthless optimization, more than any single technical advantage, was what defeated the Luftwaffe. The P-51's cooling system was vulnerable, but the strategic system that produced the P-51, the industrial capacity, the resource base, the training pipeline, the willingness to accept casualties was invulnerable to anything Germany could do by 1944. The war in Europe ended on May 8, 1945. The 8th Air Force flew its last combat mission on April 25th, a bomber strike on Pilsen escorted by P-51 seconds. No German fighters were intercepted. No Mustangs were lost to cooling system failures or any other cause. The mission was uneventful, routine, almost boring, exactly what strategic air superiority looks like when you've achieved it completely. The post-war accounting revealed numbers that validated everything Stigler and his colleagues had understood during that cold December examination. Between December 1943, when P-51 seconds first flew escort missions over Germany, and May 1945, the 8th Air Force alone flew over 213,000 P-51 sorties. Total P-51 losses in the European theatre, 2,520 aircraft to all causes. Of those losses, approximately 870 were attributed to cooling system failures following battle damage. 870 pilots died or were captured because a bullet or shell fragment punctured a coolant line, and they had 3 to 7 minutes before their engine seized. 870 families receiving telegrams that began, "The Secretary of War desires me to express his deep regret." But during those same sorties, P-51 pilots destroyed approximately 4,700 German aircraft in air combat and another 4,000 on the ground. They escorted bomber formations that dropped over 600,000 tons of ordnance on German industrial targets. They achieved air superiority so complete that by April 1945, German fighter opposition had essentially ceased to exist. The exchange was brutal but mathematically decisive. Lose 870 fighters with vulnerable cooling systems, destroy the enemy's entire air force and industrial base. From a strategic perspective, it wasn't even close. The Americans had won overwhelmingly despite, or perhaps because of, their willingness to accept a design vulnerability that killed their own pilots. Technical analysis continued after the war. The United States Strategic Bombing Survey interviewed, captured German pilots, engineers, and commanders. One section of the survey focused specifically on German assessments of Allied fighter aircraft. Multiple Luftwaffe pilots independently identified the P-51's cooling system as its primary weakness, but they also universally acknowledged that exploiting that weakness required tactical situations they increasingly couldn't create. Oberst Johannes Steinhoff, a Luftwaffe ace with 176 kills who survived the war, testified to USSBS interrogators in June 1945. "We knew where to hit the Mustang. Every pilot knew. Aim for the belly scoop, puncture the cooling system, watch them go down. But by late 1944, we couldn't get into position to make those shots. They were too fast, too high, too numerous. The vulnerability didn't matter because we couldn't exploit it anymore." German engineers who examined captured Mustangs during the war filed detailed technical reports. At least 7 separate examinations occurred between March 1944 and February 1945 at different Luftwaffe testing facilities. All reached similar conclusions. The cooling system was remarkably efficient but catastrophically vulnerable. The Meredith effect radiator installation was aerodynamically brilliant but impossible to replicate with the available German manufacturing capabilities. The aircraft represented a design philosophy fundamentally different from German practice. One report, filed by engineers at the Luftwaffe test facility at Rechlin in January 1945. Likely based on the examination Stigler participated in, included a passage that summarized the psychological impact of analyzing enemy's technology. "This aircraft demonstrates that American engineers understand principles we understand, but they implement them with a precision and consistency we cannot match. More troubling, they design with an acceptance of calculated risk that our doctrine does not permit. The result is an aircraft superior to ours in the mission parameters that matter most: range, speed, and operational flexibility. We have built fighters optimized for survival. They have built fighters optimized for victory. In total war, their approach succeeds." That passage, buried in technical documentation, captured the existential crisis German military aviation faced by late 1944. It wasn't just that American aircraft were better, it was that American thinking about aircraft design was better. The willingness to accept vulnerability in exchange for capability, to trade pilot safety for mission performance, to optimize for operational requirements rather than theoretical robustness. These represented a coherent philosophy that Germany couldn't counter. Soviet forces captured the Rechlin facility in April 1945. Most of the technical documents were destroyed before the base fell, but some survived. Soviet aviation engineers examined the reports on captured P-51 seconds with considerable interest. The Soviet Union's own fighter designs the Yak-9, La-7, and early MiG prototypes used liquid-cooled inline engines with similar vulnerability profiles. Soviet designers had made similar trade-offs for similar reasons: performance over protection. But Soviet doctrine differed from both American and German approaches. Soviet fighters were designed to be produced in massive quantities with minimal manufacturing sophistication. The surface finish was rough, tolerances were loose. Individual aircraft performance varied widely. The philosophy was overwhelming numerical superiority rather than technical excellence. Soviet pilots fought with simple tactics, aggressive commitment, and the knowledge that losses were expected and replaceable. The Americans combined technical sophistication with numerical superiority, the worst possible combination for their enemies. They built aircraft with refined engineering and manufacturing precision, then produced them in quantities that overwhelmed any qualitative advantage their opponents might achieve. The P-51 program alone resulted in over 15,000 aircraft built between 1940 and 1945. Add in other American fighter types, the P-47, P-38, and F-6F, and total production exceeded 70,000 aircraft. Germany built approximately 36,000 fighters during the same period. The Soviet Union built over 60,000. But American fighters were deployed globally. Europe, the Pacific, the Mediterranean, the China, Burma, India theater, and still achieved numerical superiority in every operational area. The industrial capacity was staggering, incomprehensible to German planners who had assumed America's industrial might was exaggerated propaganda. Reichsmarschall Hermann Göring, commander of the Luftwaffe, reportedly said in 1944, after seeing reconnaissance photos of American aircraft production facilities, "I didn't believe the intelligence reports about their production capacity. I thought they were impossible. Now, I've seen the photographs and I still don't believe them, but they're real." The P-51's cooling system vulnerability existed within that context of overwhelming industrial superiority. Yes, the design had a critical weakness. Yes, that weakness killed American pilots. But the United States could afford those losses because they were producing aircraft faster than they were losing them, training pilots faster than they were dying, and sustaining operational tempo that the Luftwaffe couldn't match. Franz Stigler recognized this during his examination of the captured Mustang. He understood the technical details, the Meredith effect radiator, the thin-walled coolant lines, the 3 to 7 minute death sentence after damage. But he also understood the larger reality those details represented. The Americans had built an aircraft that embodied their strategic advantages: industrial capacity, technological sophistication, resource abundance, and the cold willingness to accept casualties in pursuit of operational objectives. Stigler flew his Bf-109, knowing it was optimized for pilot survival in a war Germany was losing. American pilots flew their P-51 seconds, knowing they were optimized for mission success in a war America was winning. The cooling system vulnerability was real. The strategic superiority it enabled was overwhelming. In the decades after the war, the P-51 became an icon. Aviation enthusiasts celebrated its speed, range, and combat record. Air shows featured restored Mustangs performing aerobatic displays. The vulnerability that killed 870 pilots faded from popular memory, replaced by narratives of American engineering triumph and aerial supremacy. But the men who flew them and the men who fought against them remembered differently. They remembered that the Mustang was fast and fragile, deadly and vulnerable, a weapon that could dominate the sky or fall from it depending on where a single bullet struck. They remembered the white vapor trails of dying cooling systems, the desperate glides toward friendly territory, the parachutes blossoming over hostile terrain. Robert Mitchell, the crew chief who maintained P-51 seconds at Debden and watched 19 pilots from his squadron die from cooling system failures, kept a photograph on his workshop wall until he died in 2007. The photograph showed a P-51 Mustang in flight, silver finish gleaming, contrails streaming from the wingtips. On the back of the photograph, Mitchell had written in fading ink, "The best fighter we had, the most dangerous aircraft I ever worked on. Both things are true." That duality, brilliance and vulnerability, triumph and tragedy defined the P-51 Mustang more accurately than any propaganda poster or victory statistic. It was an aircraft designed by engineers who understood that war is about winning, not about perfection. It was optimized for the mission at the cost of the men who flew it. And it succeeded spectacularly because the nation that built it could afford to pay that cost. Franz Stigler died in March 2008 at age 92. In his final years, he gave several interviews about his wartime experiences. He talked about the kills, the near-death experiences, the famous escort mission where he chose not to shoot down a crippled B-17, but he also talked about the captured Mustang at Rechlin and what that examination taught him. "I learned that the Americans thought about war differently than we did," Stigler said in a 2004 interview. "We tried to build fighters that protected pilots. They built fighters that won wars. Those aren't the same thing. The P-51 had a cooling system that could be killed by a rifle bullet, but it also had the range to escort bombers to Berlin, the speed to dominate any dogfight, and the operational flexibility to fly missions we couldn't counter. They accepted the vulnerability because the capabilities mattered more. That's how you win total wars, by making hard choices and accepting the consequences." He paused, looking out the window of his Vancouver apartment at the mountains beyond. We made different choices. We prioritized pilot survival, robust construction, and defensive capability. Those were good choices for the war we thought we were fighting. But the Americans were fighting a different war, a war of industrial attrition and strategic bombing and operational reach. Their choices matched that war better than ours did. The cooling system vulnerability proves it. They knew it was there. They knew it would kill pilots. They deployed the aircraft anyway because winning mattered more than protecting individuals. The interviewer asked if Stigler thought that was immoral, sacrificing pilots knowingly. Stigler shook his head. Immoral? No. War is immoral. Once you're in it, you're just trying to win with minimum total loss of life. The Americans calculated that accepting P-51 losses to achieve air superiority would save more lives overall than any alternative. They were right. The bomber offensive shortened the war. Shorter war means fewer total deaths. The 800 pilots who died from cooling system failures? That's tragic. But it's fewer than would have died if the war lasted another year. Cold calculus. Brutal. Effective. He fell silent for a moment, then added, I shot down 7 P-51 seconds by hitting their cooling systems. 7 pilots who might have survived if their aircraft had been designed differently. I think about them sometimes, but I also think that if the P-51 had been designed differently, if it had been armoured and protected and safer for its pilots, it wouldn't have been fast enough or had enough range to do its job, and the war would have lasted longer, and more people would have died, pilots, bomber crews, civilians. So maybe those 7 pilots, and the 800 others like them, saved thousands of lives by flying a vulnerable aircraft that helped end the war faster. I don't know. I just know the Americans made a choice we didn't, and their choice won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.